Hello there, and welcome to the Relaxing Science channel. I'm so glad you're here tonight. Tonight, we're going to drift gently through the cosmos and uncover 50 secrets of the Milky Way. From distant galaxies to unseen cosmic forces, each fact is designed to spark your curiosity and help you relax, unwind, and drift into a peaceful sleep. So get comfortable, close your eyes if you like, and let's begin our journey among the stars. Look up in your imagination now, to the band of light that arches across the night sky. The Greeks called it Galaxias Kyklos, the Milky Circle. The Romans named it Via Lactea, the Road of Milk. And we've carried that name forward, the Milky Way. But this pale river of light that our ancestors wondered at is something far more extraordinary than they could have dreamed. It's not a road at all. It's our address in the cosmos, seen from the inside. You see, we live within the Milky Way galaxy. Imagine for a moment that you're standing inside an enormous cosmic disk, so large that light itself, traveling at 186,000 miles per second, would take 100,000 years to cross from one edge to the other. That's our galaxy's width. 100,000 light-years of stars, gas, dust, and mystery, all bound together in a great spiral dance. And here's something that might help you feel both wonderfully small and perfectly positioned. We're not at the center of this cosmic disk. No, we're out in the suburbs of the galaxy, about 26,000 light-years from the center, nestled in a minor spiral arm called the Orion Spur. It's a quiet neighborhood, really. Away from the crowded, energetic center where stars are born in wild profusion and ancient stellar giants end their lives in spectacular explosions. Out here, where we are, things move at a gentler pace. Our Sun, with all its planets, including our precious Earth, is traveling through this galaxy at about 514,000 miles per hour. 500,000 miles per hour. And yet, because the galaxy is so incomprehensibly large, it takes our solar system approximately 225 to 250 million years to complete just one orbit around the galactic center. The last time we were in this exact spot in the galaxy, dinosaurs hadn't even appeared yet. We were in the Permian period, and the continents were still joined together in one massive landmass called Pangaea. Think about that for a moment. We're on a cosmic carousel, spinning through the void, and yet everything feels so still, so peaceful. But the Milky Way holds more than just our solar system. Look up again in your mind's eye at that river of light, and know that you're seeing the combined glow of hundreds of billions of stars. Current estimates suggest our galaxy contains between 100 and 400 billion stars, each one a sun in its own right, many with their own families of planets. Some of those stars are ancient elders, born when the universe itself was young. Others are stellar infants, still wrapped in the nebulous clouds of their birth. And here's a secret that deepens the mystery. For all those billions of stars, most of what makes up the Milky Way is something we cannot see. About 90% of our galaxy's mass is dark matter, an invisible substance that we can only detect through its gravitational influence on the things we can see. It's like the Milky Way is an iceberg, and the stars we observe are just the gleaming tip above water. Below, in the cosmic depths, vast quantities of something unknown hold everything together, keeping our galaxy from flying apart as it spins through space. At the very heart of our galaxy, 26,000 light-years away from us, lies something both terrifying and magnificent. There, in a region called Sagittarius A*, pronounced Sagittarius A star, lurks a supermassive black hole, weighing as much as 4 million of our suns. It sits there in the darkness, a gravitational monster so powerful that nothing, not even light, can escape once it crosses the black hole's event horizon. And yet, it's quiet now, dormant, feeding only occasionally on the occasional unfortunate star that wanders too close. Billions of years ago, this black hole may have been far more active, consuming matter in great luminous feasts, making the center of our galaxy blaze across the cosmos. Now it rests, a sleeping giant at the heart of our galactic home, its presence felt through the rapid orbits of stars that dance around it like moths around a flame they can never see. But you don't need to worry about that distant darkness. Not tonight. You're here, safe on Earth, orbiting a stable star, in a calm arm of the galaxy where life has had billions of years to flourish. The Milky Way is your cradle, your home, your context in the infinite expanse. And as you drift towards sleep, imagine yourself as a tiny point of consciousness in this vast spiral, connected to everything, to every star that's ever burned, to every galaxy that neighbors ours, to the very fabric of space-time itself. Let's drift deeper now into the story of our galaxy, peeling back the layers of time and space like turning the pages of the universe's oldest book. The Milky Way wasn't always here, you know. It wasn't born fully formed. Our galaxy is approximately 13.6 billion years old, nearly as old as the universe itself, which began 13.8 billion years ago in that first explosive moment we call the Big Bang. In the grand cosmic timeline, the Milky Way emerged early, coalescing from clouds of primordial hydrogen and helium in the ancient darkness, when the universe was still in its infancy. And it grew the way many things in nature grow, not smoothly, but through merger and acquisition. Over billions of years, our galaxy has consumed dozens of smaller galaxies, absorbing them into its spiral structure. Even now, as you rest here, the Milky Way is in the process of devouring several dwarf galaxies. The Sagittarius dwarf elliptical galaxy is being slowly torn apart by our galaxy's gravitational pull, its stars gradually joining the Milky Way's vast stellar population. It's a gentle violence, really, a cosmic dance that plays out over hundreds of millions of years, imperceptible in a human lifetime, but inevitable across the ages. If you could speed up time and watch our galaxy from the outside, you'd see it's not static at all. The Milky Way is a spiral galaxy, one of the universe's most beautiful structures. Four major spiral arms sweep out from the central bulge, like cream stirred into coffee, or water spiraling down a drain in reverse. These arms, Perseus, Norma, Scutum Centaurus, and Cygnus, are not solid structures but density waves, regions where stars and gas clouds naturally gather as they orbit the galactic center. They're like traffic jams on a cosmic highway, places where matter accumulates and new stars are born in brilliant nurseries of gas and dust. Our own solar system, remember, sits in that minor arm called the Orion Spur, between the Perseus and Sagittarius arms. It's a bridge, a connector, a place where the spiral pattern is less defined. And perhaps that's fitting, a quieter place for a planet where life could emerge and consciousness could evolve to contemplate its own origins. Now, let your mind wander to the space between the stars. It seems empty, doesn't it? A void. But that's an illusion. The interstellar medium, as astronomers call it, is filled with gas and dust, just extraordinarily thinly spread. On average, there's only about 1 atom per cubic centimeter in interstellar space. To put that in perspective, the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. The space between stars is a vacuum far more perfect than anything we can create on Earth. And yet, across the vast distances of the galaxy, all that tenuous gas and dust adds up to billions of times the mass of our Sun. It's the raw material from which new stars are born, the ashes of stars that died long ago, recycled endlessly in the great cosmic circle of creation and destruction. And here's something that connects you directly to the Milky Way's ancient past. Every atom in your body heavier than hydrogen was forged in the heart of a star. The calcium in your bones, the iron in your blood, the carbon that forms the basis of all organic molecules, these elements were created billions of years ago in stellar furnaces, in stars that lived and died before our Sun was born. When those ancient stars exhausted their fuel, they exploded as supernovae, scattering their enriched contents across the galaxy. That stardust mixed with clouds of gas, and from those enriched clouds, our solar system eventually formed. The galaxy rotates, but not like a solid disk. Different parts rotate at different speeds, a phenomenon called differential rotation. The inner regions spin faster, completing their orbits more quickly, while the outer edges take their time. Near the galactic center, stars might complete an orbit in just tens of millions of years. Out where we are, it takes that 225 million years we mentioned earlier. And further out still, in the remote outer reaches, stars drift even more slowly through their endless circuits. This differential rotation is part of why the spiral arms exist at all, and why they maintain their shape over billions of years despite the galaxy's rotation. It's a delicate gravitational choreography, one that astronomers are still working to fully understand. But perhaps the most humbling fact is this: the Milky Way isn't alone. It's not an island floating in empty cosmic space. Our galaxy is part of something called the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group spans about 10 million light-years and includes our galaxy, the Andromeda Galaxy, which is actually larger than the Milky Way, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. We're all neighbors in this small corner of the universe, all moving through space together. And the Local Group itself? It's just one small neighborhood in an even larger structure called the Virgo supercluster, which contains thousands of galaxies spread across 110 million light-years. We're nested within structures of ever-increasing scale, like Russian dolls of cosmic architecture, each layer revealing a new level of organization in the universe's grand design. As you breathe slowly and let yourself relax even deeper, imagine the Milky Way not as a fixed thing, but as a living system, growing, changing, moving through space, part of a cosmic community, and giving birth to stars and worlds and, at least once, to conscious beings who can look up and wonder at it all. Let's turn our attention now to the light itself, that gentle glow you see when you look up at the night sky on a clear, dark evening, far from city lights. When you see the Milky Way stretching across the heavens, you're looking toward the galactic plane, the flat disk where most of our galaxy's stars reside. The reason it appears as a band of light is simply a matter of perspective. We're inside the disk, looking through it edge on, so we see many more stars in that direction than we do when we look above or below the galactic plane. It's like standing in a forest and looking through the trees horizontally. You see many more trunks than if you look straight up at the sky through the canopy. But here's something remarkable. Despite the hundreds of billions of stars in our galaxy, the average distance between stars is enormous. If our sun were the size of a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand about 4 miles away. The Milky Way is mostly empty space, a vast darkness punctuated by distant points of light. Stars are islands separated by oceans of void, and yet, from our perspective, they seem crowded together, close enough to form patterns and tell stories. The center of our galaxy, where that supermassive black hole dwells, is hidden from our direct view. Between us and the galactic core lies an enormous amount of dust, cosmic soot, really, the remnants of dead stars and the birthplaces of new ones. This dust absorbs visible light, obscuring our view of the galactic heart in optical wavelengths. For most of human history, we couldn't see what lay at the center of our own galaxy. But modern astronomy has given us new eyes. Using infrared telescopes, which can peer through the dust, and radio telescopes that detect different wavelengths altogether, we've finally glimpsed the crowded, energetic region at the Milky Way's core, where stars orbit so close to the central black hole that they complete their circuits in mere years rather than millions of years. Now, let your thoughts drift to the concept of time, and how differently it flows across the galaxy. The stars you see when you look at the Milky Way aren't showing you the galaxy as it is now, they're showing you the galaxy as it was. Light travels fast, but the galaxy is so large that even light takes time to cross it. When you look at a star 1,000 light years away, you're seeing light that left that star 1,000 years ago, during Earth's Middle Ages. That star might not even exist anymore. It could have exploded as a supernova centuries ago, but the light of that explosion hasn't reached us yet. In a real sense, when you gaze at the Milky Way, you're looking at different eras of galactic history all at once, layered together in the present moment. The galaxy isn't just moving through space randomly, it has a destination. The Milky Way, along with all the galaxies in the local group, is being pulled through space at about 1.3 million miles per hour towards something astronomers call the Great Attractor. This is an enormous concentration of mass located about 150 million light-years away, in the direction of the constellations Hydra and Centaurus. We can't see it directly because it lies behind the zone of avoidance, a region of the sky obscured by the Milky Way's own disk. But we can measure its gravitational influence, the way it pulls on our galaxy and thousands of others. It's like being in a river, feeling the current, knowing there's something downstream even if you can't see it yet. And here's something that might bring both wonder and a touch of bittersweet beauty to your thoughts. The Milky Way won't remain separate forever. In about 4.5 billion years, our galaxy will collide with the Andromeda Galaxy, our nearest large galactic neighbor, currently speeding toward us at about 250,000 miles per hour. When they meet, it won't be a violent crash in the way you might imagine. Remember, galaxies are mostly empty space. The stars are so far apart that very few will actually collide. Instead, the two galaxies will pass through each other like ghosts, their gravitational fields intertwining, pulling and stretching each other into new shapes. Over the course of a few billion years, they'll merge into a single, larger elliptical galaxy that astronomers have playfully nicknamed Milky. By that time, our Sun will be nearing the end of its life, expanding into a red giant. Earth itself may not survive. But whatever happens, the atoms that once made up our world, the elements forged in ancient stars, will continue on, incorporated into the new galaxy, perhaps someday becoming part of new worlds, new possibilities. The Milky Way, in its current form, is temporary. Everything in the universe is temporary. And yet, there's something peaceful about that, isn't there? The galaxy is a process, not a thing. It's a 4-billion-year-old dance that will eventually transform into something new. And you're here, now, in this particular moment of the dance, conscious and aware, able to understand and appreciate your place in it. Speaking of places, the galaxy contains an estimated 100 billion to 400 billion planets, at least one planet for every star, on average, and many stars have multiple worlds. Among those hundreds of billions of planets, astronomers estimate that billions could be Earth-sized worlds orbiting in their star's habitable zone, where conditions might be right for liquid water and, potentially, life. We call these exoplanets, worlds beyond our solar system, and we've already discovered thousands of them with our telescopes. Out there, somewhere in the Milky Way, there might be other beings looking up at their night sky, seeing their own version of the galactic band of light, wondering if they're alone. Or perhaps we are unique, the only place in the entire galaxy where matter has organized itself into consciousness and built civilizations and wondered about its origins. Either answer, that we're one of many, or that we're utterly alone, is profound. Either way, the galaxy contains multitudes, possibilities folded into the space between stars. As your breathing slows and deepens, as your mind settles into rest, hold this thought: the Milky Way is both your home and your context. It's the stage on which the human story has unfolded, the vast arena that contains every person who has ever lived, every dream, every discovery, every moment of joy and sorrow in human history. All of it has happened here, in this one small corner of one galaxy among billions. And tomorrow, when you wake, the galaxy will still be here, spinning slowly through the darkness, ancient and patient, holding you in its spiral embrace. Let's descend now into one of the galaxy's most beautiful mysteries, the stellar nurseries where new stars are born, even as you rest here in the quiet darkness. Scattered throughout the Milky Way are vast clouds of gas and dust called nebulae. These clouds, some of them hundreds of light years across, are the maternity wards of the galaxy. One of the most famous is the Orion Nebula, visible even to the naked eye as a fuzzy patch in Orion's sword, located about 1,344 light-years from Earth. Inside this glowing cloud, right now, thousands of new stars are forming, condensing from the swirling gas and dust like dewdrops forming on a spider's web. These stellar infants are so young, some only a few 100,000 years old, that they're still surrounded by the disks of material from which planets will eventually form. We're witnessing creation itself, frozen in light that left those nurseries over a millennium ago. The process is slow and patient, like everything cosmic. A cloud of gas begins to collapse under its own gravity, perhaps triggered by the shockwave from a nearby supernova or the gravitational nudge from a passing star. As it collapses, it fragments into smaller clumps, each clump spinning and heating as it contracts. Over millions of years, the center of the clump grows hotter and denser until finally, miraculously, it reaches the temperature and pressure needed to ignite nuclear fusion. Hydrogen atoms begin fusing into helium, releasing tremendous energy, and a star is born, a new point of light in the galaxy's vast tapestry. Our own sun was born this way, about 4.6 billion years ago, in a nebula that no longer exists. The shockwave from a nearby supernova, perhaps containing the heavy elements that would later become part of Earth and part of you, may have triggered the collapse of the cloud that became our solar system. That ancient star that exploded, seeding our stellar nursery with the materials for rocky planets and living beings, is long gone now. But its legacy lives on in every atom of your body. Now, consider the variety of stars scattered across the galaxy. They come in a spectacular range of sizes, colors, and temperatures. The smallest stars, called red dwarfs, are only about 8 to 50% the mass of our Sun. They burn their fuel so slowly, so efficiently, that they can live for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever been born is still alive today. These dim, cool stars are actually the most common type in the Milky Way, making up about 70 to 75% of all stars. They're the wallflowers of the galaxy, quiet, unassuming, incredibly long-lived. At the opposite extreme are the supergiant stars, monsters that dwarf our Sun. Take Betelgeuse, the red supergiant in the constellation Orion, visible as a distinctly reddish star to the naked eye. Betelgeuse is so enormous that if you placed it where our Sun is, its surface would extend past the orbit of Mars. It contains enough material to make about 16 to 19 suns, and it shines with the light of about 100,000 suns. But such brilliance comes at a cost. Betelgeuse is burning through its fuel at a prodigious rate. It's only about 10 million years old, incredibly young by stellar standards, and it's already near the end of its life. Someday soon, in cosmic terms, perhaps tomorrow, perhaps 100,000 years from now, it will explode as a supernova. When it does, it will briefly outshine the entire galaxy and be visible from Earth even in daylight. The galaxy is filled with stars in every stage of life. There are infant stars still hidden in their birth clouds, adolescent stars like our Sun in the prime of their lives, aging stars swelling into red giants, and the remnants of dead stars, white dwarfs, neutron stars, and black holes. The Milky Way is a cosmic ecosystem, constantly recycling matter from death to birth and back again. Let your mind drift now to the structure beneath the visible, the dark matter halo that surrounds our galaxy. Remember, the stars and gas we can see make up only about 10% of the Milky Way's mass. The rest is dark matter, arranged in an enormous, roughly spherical halo that extends far beyond the visible disk. This dark matter halo is perhaps 10 times wider than the luminous galaxy we can observe, reaching out 500,000 light-years or more from the galactic center. We're inside this halo right now, embedded in it, dark matter particles passing through your body and through the Earth at every moment. We can't feel it, can't see it, can't interact with it except through gravity, but it's there, holding the galaxy together, keeping the stars from flying apart as the galaxy rotates. What is dark matter? We honestly don't know yet. It's one of the great unsolved mysteries of modern science. We know it exists because of how galaxies rotate and how clusters of galaxies move, but its fundamental nature remains hidden. Perhaps it's made of particles we haven't discovered yet. Perhaps it's something even stranger. For now, it remains a question mark in the cosmic equation, a reminder that for all we've learned, the universe still holds secrets. As you sink deeper into rest, imagine the full three-dimensional structure of the Milky Way. The thin disk where most stars reside, the central bulge swelling at the core, the spiral arms winding outward, and above and below the disk, something called the stellar halo, a roughly spherical distribution of old stars and ancient star clusters called globular clusters. These globular clusters are among the oldest objects in the galaxy, some containing stars that are 12 to 13 billion years old, born when the Milky Way itself was young. Each cluster contains hundreds of thousands of stars packed into a sphere only about 100 light-years across, much denser than our neighborhood. If Earth orbited a star in a globular cluster center, the night sky would be filled with thousands of bright stars, casting shadows and making true darkness nearly impossible. It would be a sky of perpetual twilight, beautiful and strange. These ancient clusters orbit through the galactic halo in long elliptical paths, swooping down through the disk and back out again, completing their orbits over hundreds of millions of years. They're like cosmic elders, witnesses to nearly the entire history of our galaxy, carrying in their stars the chemical signature of the early universe. Everything is connected: the dust, the stars, the dark matter, the black hole at the center, the spiral arms, the clusters, all moving together in gravitational harmony, all part of one vast, ancient, evolving system. And here you are, nestled within it, a brief flicker of awareness in the long cosmic night, precious and improbable and real. Now let's explore something truly mesmerizing: the way the galaxy breathes, the way it moves and pulses with energy across the vast spans of space and time. The Milky Way isn't silent. If we could hear it, the galaxy would be filled with a symphony of electromagnetic radiation, radio waves, microwaves, infrared light, visible light, ultraviolet, X-rays, and gamma rays. These aren't sounds, exactly, but they're waves of energy rippling through space. Radio telescopes can detect emissions from hydrogen gas spread throughout the galaxy, creating what astronomers call the 21-centimeter line, a specific radio wavelength that hydrogen naturally emits. By mapping this radio emission, we've been able to trace the spiral arms of the Milky Way and understand its structure, even from our position buried within the disk. It's like using sonar to map the ocean floor while you're swimming in the depths. One of the most energetic and mysterious phenomena in our galaxy are magnetars, a special type of neutron star with a magnetic field so intense it defies everyday comprehension. A neutron star is already extraordinary, the collapsed core of a massive star, packed so densely that a teaspoon of its material would weigh about 1 billion tons on Earth. But magnetars take this to an extreme. Their magnetic fields are quadrillion times stronger than Earth's magnetic field, so powerful that if a magnetar existed halfway between Earth and the Moon, it would erase the magnetic strip on every credit card on our planet and potentially pull the iron from your blood. The Milky Way contains perhaps a dozen known magnetars, scattered through the galactic disk, occasionally flaring with bursts of X-rays and gamma rays, cosmic lighthouses of incredible power. Let's drift now toward the edges of the galaxy, to a region we rarely think about. Beyond the main disk, at distances of 130,000 to 300,000 light-years from the galactic center, orbit two small irregular galaxies called the Large and Small Magellanic Clouds. These are satellite galaxies, companions to the Milky Way, visible as fuzzy patches in the southern hemisphere's night sky. The Large Magellanic Cloud contains about 30 billion stars, substantial, but dwarfed by our galaxy's hundreds of billions. These Magellanic Clouds are slowly being disrupted by the Milky Way's gravitational pull, leaving behind a stream of gas called the Magellanic Stream that stretches across 500,000 light-years of space. It's like a cosmic breadcrumb trail, showing the path these small galaxies have taken as they orbit our own. Within our galaxy lies a structure that has puzzled astronomers for years, the Fermi bubbles. Discovered in 2010 using the Fermi Gamma-ray Space Telescope, these are two enormous bubbles of high-energy gamma rays extending 25,000 light-years above and below the galactic center. That's half the diameter of the entire galactic disk, protruding perpendicular to the spiral like cosmic soap bubbles. These bubbles may have been created by ancient bursts of star formation in the galactic center, or perhaps by periods when our central supermassive black hole was more active, devouring matter and ejecting tremendous jets of energy. They're evidence that our galaxy's center was once far more violent and energetic than it is today, a reminder that even galaxies have turbulent histories. The rotation of the Milky Way has revealed something unexpected and profound. The galaxy spins too fast. Based on the visible matter we can see, all the stars and gas, the outer regions should be rotating much more slowly than they actually are. In fact, the outer parts should barely be bound to the galaxy at all. But they're not flying away. Instead, they rotate almost as quickly as the inner regions. This observation, first made by astronomer Vera Rubin in the 1970s, was one of the key pieces of evidence for dark matter's existence. Something invisible, something we cannot see or touch, must be holding the galaxy together, providing additional gravitational force. The dark matter halo we mentioned earlier isn't just theoretical, it's necessary. Without it, galaxies like ours couldn't exist in the form we observe. Consider for a moment the magnetic field of the Milky Way itself. Yes, the entire galaxy has a magnetic field, threaded through the interstellar medium like invisible fibers running through cotton. This galactic magnetic field is incredibly weak by everyday standards, about 1,000,000 times weaker than a refrigerator magnet, but across the vast scales of the galaxy, it has profound effects. It influences how gas clouds collapse to form stars, shapes the paths of cosmic rays traveling through interstellar space, and creates beautiful structures we can observe with radio telescopes. The field follows the spiral arms, wrapping around the galactic center, a ghostly architecture underlying the visible structure of stars and nebulae. The stars themselves move in complex patterns through the galaxy. Our Sun, for instance, doesn't just orbit the galactic center in a simple circle. As it travels around the galaxy, it also oscillates up and down through the galactic plane, like a horse on a carousel that also moves up and down. Our solar system crosses through the midplane of the galactic disk approximately every 30 million years or so. Some scientists have speculated, though it remains controversial, that these crossings might correlate with periods of increased comet impacts on Earth or even mass extinctions, as we pass through denser regions of gas and dust. The galaxy, in this view, isn't just our home but an active participant in Earth's history, its rhythms potentially influencing the evolution of life itself. Deep in the disk, hidden among the hundreds of billions of ordinary stars, there are hypervelocity stars, stellar outcasts traveling so fast they're escaping the Milky Way entirely. These stars are moving at speeds of 700 kilometers per second or more, fast enough to overcome the galaxy's gravitational pull. Most were likely ejected from the galactic center in gravitational interactions with the supermassive black hole, a binary star system that wandered too close, with one star captured by the black hole and the other flung outward at tremendous speed, like a gravitational slingshot. These runaway stars will eventually leave the Milky Way completely, spending the rest of their lives drifting through intergalactic space, forever separated from the galaxy that birthed them. There are perhaps 1,000 such stars scattered through the Milky Way, each one carrying a story of close encounter and violent ejection. And you are here, in this moment, part of this grand cosmic dance, held gently by gravity, illuminated by starlight that has traveled across the years to reach you. Let's turn our attention now to the edges of perception, to the things we've only recently discovered, the secrets the Milky Way has been keeping for billions of years. In 2020, astronomers made a startling discovery at the heart of our galaxy, a structure they named the Radcliffe Wave. This is an enormous, undulating chain of stellar nurseries, stretching nearly 9,000 light-years long, waving through space like a ripple on water. It contains about 3 million solar masses worth of gas, and it's the largest coherent structure of star-forming regions we've ever identified in the Milky Way. What's remarkable is that we live quite close to it. It begins just 500 light-years from our Sun. For all of human history, we've been swimming beside this cosmic wave, unaware of its existence, until our technology finally became sophisticated enough to map it. The galaxy keeps revealing new layers, new structures we never knew were there. Now, imagine looking at the Milky Way not with optical telescopes, but with instruments that detect neutrinos, ghostly particles that barely interact with matter at all. Trillions of neutrinos pass through your body every second, most of them coming from the Sun, but also from distant supernovae and other energetic events across the galaxy. Neutrinos can pass through entire planets as if they weren't there. The Milky Way is constantly bathed in a sea of these particles, a hidden layer of reality that we're only beginning to observe. Deep underground and beneath Antarctic ice, scientists have built detectors to catch these elusive messengers. Each neutrino they detect tells a story of a violent event somewhere in the cosmos, a supernova explosion, a black hole feeding, processes so energetic they create particles that traverse the entire galaxy without stopping. Let your thoughts drift to the question of habitability, to the concept of the galactic habitable zone. Not all parts of the Milky Way are equally suitable for life. Too close to the galactic center, and the environment becomes hazardous, higher levels of radiation, more frequent supernovae, greater gravitational disruptions from passing stars. Too far out, and there aren't enough heavy elements, the carbon and oxygen and iron needed to build rocky planets and, eventually, living organisms. We live in what some astronomers call the Goldilocks zone of the galaxy, not too close, not too far, but just right. Our position in the Orion Spur, about 26,000 light-years from the center, may be one of the safest, most stable neighborhoods in the entire galaxy, a place where life has had the billions of years of relative peace necessary to evolve from simple chemistry to consciousness. The Milky Way contains structures called stellar streams, long, thin trails of stars stretched across the sky. These are the remnants of dwarf galaxies and globular clusters that have been torn apart by the Milky Way's gravitational forces. As these smaller systems orbit our galaxy, the tidal forces stretch them out, pulling stars away like taffy until all that remains is a thin river of stars following the orbit of their destroyed parent. More than a dozen such streams have been discovered, ghost trails marking the graves of devoured galaxies, slowly being absorbed into the Milky Way's stellar population. It's galactic archaeology, reading the history of our galaxy and the debris of its past collisions and conquests. Deep within the disk, astronomers have identified what they call molecular clouds, enormous concentrations of molecular hydrogen, the coldest, densest regions of the interstellar medium. These clouds, some containing hundreds of thousands of times the mass of our Sun, are dark and opaque, completely blocking visible light. Inside them, temperatures drop to just 10 or 20 degrees above absolute zero, among the coldest places in the universe. And yet, paradoxically, these frigid clouds are where stars are born. The darkness and cold allow gravity to win, pulling matter together until fusion ignites and heat and light emerge. One of the most massive of these structures is the Sagittarius B2 complex, located near the galactic center, containing enough material to make 3 million stars like our Sun. It's also, oddly enough, the place where complex organic molecules have been detected, including ethanol and chemicals that give raspberries their flavor. The galaxy is stranger than we can imagine. Consider the timescales on which the galaxy operates. A human lifetime is about 80 years, if we're fortunate. Recorded human history spans perhaps 5,000 years. Our species, Homo sapiens, has existed for roughly 300,000 years. But the Milky Way has been evolving for 13.6 billion years, more than 45,000 times longer than humanity has existed. If you compress the entire history of the galaxy into a single year, with the galaxy forming on January 1st, our solar system wouldn't form until late August. Life on Earth wouldn't appear until early September. Dinosaurs would arrive in late December and go extinct on December 30th. All of human civilization, the pyramids, the Roman Empire, the Renaissance, the modern world, would flash by in the final few seconds before midnight on December 31st. We are so new to this ancient system, such recent arrivals to this cosmic home. The galaxy is also home to mysterious objects called pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the neutron star spins, these beams sweep through space like a lighthouse, and if Earth happens to be in the path of the beam, we detect regular pulses of radio waves, X-rays, or gamma rays. Some pulsars spin hundreds of times per second, making them among the most precise natural clocks in the universe. The fastest known pulsar, PSR J1748-2446 AD, rotates 716 times per second, its surface moving at roughly 24% of the speed of light. These cosmic lighthouses are scattered throughout the Milky Way, silent sentinels marking the graves of massive stars, their precise timing helping astronomers test theories of gravity and probe the nature of matter itself. Finally, let's contemplate something both humbling and extraordinary: the cosmic perspective the Milky Way provides. Every human being who has ever lived, every king and peasant, every artist and warrior, every saint and sinner, has lived out their entire existence on one small planet, orbiting one ordinary star, in one minor arm of this galaxy. All of human drama, all our wars and loves, our triumphs and tragedies, have taken place in an almost inconceivably tiny corner of this vast system. And yet, we've managed to understand so much. We've mapped the galaxy, measured its mass, traced its history, and predicted its future. We've sent our spacecraft beyond the solar system, carrying messages into the wider galaxy. We've turned our telescopes on the cosmos and deciphered its secrets, one photon at a time. In the mere instant of cosmic time that humans have been aware of the universe, we've come so far. As you rest now, feeling your breath slow and your body relax, know that you're connected to all of this, to the spiral arms and star clusters, to the dark matter and distant nebulae, to the history and future of this great wheeling disk of stars. The atoms in your body were forged in stellar furnaces. The elements that make up your bones and blood were scattered by dying stars. You are, in the most literal sense, a way for the Milky Way to know itself. Let us journey now into the realm of cosmic chemistry, to the story of how the galaxy creates the building blocks of worlds and life itself. When the universe began, it contained only the simplest elements: hydrogen, helium, and trace amounts of lithium. That was all. No carbon, no oxygen, no iron, no gold. Everything heavier than those primordial elements has been manufactured inside stars. The Milky Way is a vast chemical factory, and it's been in operation for over 13 billion years. Each generation of stars takes in simple elements, fuses them into heavier ones, and then returns those enriched materials to the interstellar medium when the star dies. Astronomers call this increasing chemical complexity metallicity, and they can trace the metallicity of stars throughout the galaxy. The oldest stars, those born when the galaxy was young, have very low metallicity. They're made almost entirely of hydrogen and helium. Our Sun, by contrast, is a third-generation star, enriched with all the elements created by previous stellar generations. This metal-rich composition was essential for forming the rocky planets of our solar system, including Earth. The galaxy's disk isn't uniform. It has a structure astronomers call the metallicity gradient. Stars and gas closer to the galactic center tend to be more metal-rich than those in the outer regions. This makes sense. The center has had more generations of star formation, more supernovae enriching the gas, a longer and more intensive history of chemical evolution. As you move outward from the center, the metallicity gradually decreases. We can read this gradient like a book, learning about the history of star formation and enrichment across different regions of the galaxy. It's another kind of galactic archaeology, written not in the positions of stars but in their chemical composition. Now, let your mind wander to the concept of galactic rotation curves, the mathematical description of how fast different parts of the galaxy rotate. In our solar system, planets farther from the Sun orbit more slowly, following what's called Keplerian motion. Mercury orbits the Sun in just 88 days, while distant Neptune takes 165 Earth years. We'd expect galaxies to behave the same way. Stars farther from the center should orbit more slowly. But they don't. Beyond a certain point, the rotation speed stays roughly constant no matter how far out you go. This flat rotation curve was one of the first clear signs that something invisible, dark matter, must be present, providing additional gravitational pull to keep those outer stars moving faster than they should. The galaxy's visible matter alone cannot explain what we observe. The dark matter halo extends far beyond the visible stars, invisibly dominating the galaxy's mass and motion. In the disk of the Milky Way, embedded in the spiral arms, are regions called HII regions, pronounced H2 regions. These are clouds of ionized hydrogen gas, glowing pink or red, heated and illuminated by young, hot, massive stars that have recently formed within them. The ultraviolet radiation from these newborn stars is so intense it strips electrons from hydrogen atoms, ionizing the surrounding gas and making it glow. These regions are among the most beautiful objects in the galaxy when photographed, vast clouds of luminous gas in shades of red and pink, often studded with bright blue stars. They're signposts of recent star formation, markers of where the galaxy is currently giving birth to new suns. And they're scattered throughout the spiral arms, concentrated in the regions where gas is densest and star formation most active. Consider, too, the phenomenon of stellar metallicity in another context, the study of population 1, population 2, and the hypothetical population 3 stars. Population 1 stars are metal-rich, young stars like our Sun, found primarily in the galactic disk. Population 2 stars are metal-poor, older stars, found in the galactic halo and in globular clusters. And population 3 stars, which have never been directly observed, would be the very first generation of stars, formed from the pristine hydrogen and helium of the early universe, containing no metals at all. These first stars would have been massive, short-lived, and would have ended their lives in spectacular supernovae that seeded the universe with the first heavy elements. Somewhere in the distant universe, perhaps, we might still find evidence of these primordial giants. But in our galaxy, they're long gone, their legacy written in every star born since. The Milky Way's spiral arms are not just regions of enhanced star formation, they're also regions where supernovae are more frequent. A supernova is the explosive death of a massive star, an event so energetic that for a brief time, a single dying star can outshine an entire galaxy of hundreds of billions of stars. These explosions release tremendous amounts of energy and scatter newly forged elements into the interstellar medium. The Milky Way experiences a supernova roughly once every 50 years on average, though many are hidden from our view by dust and distance. The last supernova visible to the naked eye from Earth was in 1604, Kepler's supernova, observed by Johannes Kepler and others. We're overdue to witness another one, and when it happens, it will be a spectacular sight, a new star appearing in the sky where none existed before, perhaps bright enough to be visible even in daylight for weeks. Let's explore the concept of the galaxy's disk thickness. The main stellar disk of the Milky Way is remarkably thin relative to its diameter, about 2,000 light-years thick compared to 100,000 light-years across. That's a ratio of 1 to 50, like a DVD or a vinyl record. This thinness is maintained by the star's orbital motions. They're all moving in roughly the same plane, in roughly the same direction, like cars on a cosmic highway. But there's also a thicker disk component, extending about 3,000 to 4,000 light-years above and below the main plane, composed of older stars with more random motions. These stars have been kicked into higher orbits over time by gravitational interactions with massive gas clouds or other stars. The galaxy, in this sense, has layers: the thin disk of young, orderly stars, and the thick disk of older, more scattered stars, each telling a different part of the galaxy's story. Finally, consider the concept of stellar nucleosynthesis, the process by which stars create elements. In the core of a star like our Sun, hydrogen fuses into helium. In more massive stars, as they age, helium fuses into carbon and oxygen. In the most massive stars, the fusion process continues. Carbon fuses into neon and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. But iron is the end of the line. Fusing iron consumes energy rather than releasing it, so when a massive star's core becomes iron, fusion stops, the core collapses, and the star explodes as a supernova. In that explosion, in the extreme conditions of collapsing matter and rebounding shock waves, elements heavier than iron are created: gold, silver, uranium, platinum. Every atom of gold ever found on Earth was created in a supernova or in the collision of two neutron stars, events of unimaginable violence and energy. The jewelry people wear, the electronics we use, the precious metals we value, all of them are the debris of stellar death, scattered across the galaxy and eventually incorporated into new worlds. As your breathing becomes slower and deeper, as the edges of waking thought begin to blur into the gentle embrace of sleep, hold this image. You are made of elements created in the hearts of stars, scattered by supernovae, gathered into clouds, condensed into a planet, organized into living cells, and now aware, capable of tracing your own atomic ancestry back through the history of the galaxy. You are the universe contemplating itself, a brief moment of self-awareness in the great cosmic story. Rest now, knowing that the same processes that built the galaxy also built you, that you are as much a part of this vast system as any star or nebula. Thank you for spending this time with me here on Relaxing Science. I hope this journey through the mysteries of the universe brought you calm, comfort, and a sense of wonder. If you enjoyed this video, you're always welcome to subscribe to the channel and gently tap the bell icon, so you don't miss future relaxing science stories. For now, take a slow breath, stay comfortable, and allow yourself to drift into a peaceful sleep. Good night, and I'll see you again among the stars.